we'll take a dummy input file and then do this listening. Okay. 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 Sorry. And then let's play this video. Okay, so now we'll first get the precipitate count. So if we click on this, yeah, so it takes a few moments. Yeah. So as you saw in today's second session as well, the CUDA GPU session. So there also we showed this kind of stuff. So here also we are again verifying the same thing, that initially we started with some 500 precipitates, and then after coarsening it reduces down to about 200. Yeah. Yeah. So the total the end precipitate count is written here 211. And we can play this as well. So if we play, we can see at every time step how many precipitates are there. So this is something nice that to see. Okay. And then of course you can save this image. So I'll save this image here outside. So precipitate count. So we'll just go back and check whether we have that file. So I just save this plot and see, you can get the plot as well. Okay. And that plot you could get for a particular time step, or you could get it for multiple time steps as well. And then let's look at the precipitate size. Okay. Again, we have to wait for a few seconds. Yeah. So we have here now. So as I already told, these are the coordinates of all the precipitates that we have, the approximate centers, and then the radius, major axis, minor axis. And then we can plot any of these data. So we can select any of these columns. Suppose I selected the radius column and I'll click on plot with time. So we can get a plot of radius with respect to the number of iterations or the time. Okay. And again, we can save this plot as well. And let's do it again. And then if you want to tweak something here, that also can be done. Okay. Yeah. And then if you want the plots of all of these columns that we have here, then you can just click on plot all, and you can get all these plots: area, radius, aspect ratio, and then major axis. Then moving on to the area measurement. So okay. So here, I mean, this is mostly same as the the previous table, just that here we have one more extra thing, that is area, and we can plot it with time. So yeah, so we can get the area this way. And then we can look at the phase fraction. Again, so whenever we click on any option, we have to wait for a few seconds. Okay, so here we can see the phase fractions.
This is of the alpha phase, right?
Yeah, you can speak louder.
Yeah, this is for the alpha phase, and then if you are interested in the liquid phase, then you can switch it.
Yeah. So now we have to, so I switch to liquid and I'll click on the phase fraction again. Yeah, so this is the liquid fraction that we have, and then again you can get it with respect to time as well. So you can play and you can see these point moving. Okay, and then moving on to the next thing, that is volume. So we'll again go back to alpha. The kind of same. Yeah. So we have the total volume of alpha. So out of all the, so our domain has some volume. So and then so it calculates how much is the volume of all the alpha phase that we have in the domain. And then similarly we can find the surface area. Yeah. So here we can we have surface area as well. So I mean, as you can see, we can find several things with the coarsening simulations. We can find the area, we can find the precipitate counts, precipitate size, and then phase fraction, surface area, etc. And here we can see that the surface area reduces with time. Okay. That is what would happen in the coarsening. And then there are some other things that you could do. So we saw that this option, through this option, we can import an in file. Through this, we import the VTK, and through this option, we can save. So here on the left hand side, we have this image. We can save this image, export all the images or an image for a particular time step using this. So you click on this, and if you don't check this option and just click on convert, it will create an image of this particular time step. So you can see we are at the 137 time step and it has created an image for the 137 time step. So we'll just go and check this image. So we have it here. Yeah. So we can have, so we can save the images of the plots as well as the simulation data. Then similarly, if you click on this import save images and then click on include all time steps, then it will save the images for all the time steps. The next thing is you can export all the data as CSV file as well. So let's do that. So if you don't specify any path, it will just save it at the location where the VTK files are or your data files are stored. So again, we have 137 CSV. Okay, so this file. Okay, so it's a pretty large file because we have the data of the, it's taking time.
There are around 1 million cells.
Yeah. So if we go to the very end. Yeah. So it's a pretty large file, so it's opening slow.
Yeah, you can see some non-zero values.
Yeah. cross 1000. So for each of the point, I mean each of the cell, we have the data of the phase or the phi value that we have.
These values are at the interface, right? Which is in between 0 and 1.
Yeah. Okay. Then we have. Okay. So and then you already saw how to convert the H5 to BTK. So it takes some time, so that's why we'll not go into that. Then I'll just clear the screen and we'll move on to the next case. So next we'll look at dendrite simulation. So again, we will open the first VTK file, that is the 0 at time VTK file. Okay. And then let's play this. So here you can see there is a very, I mean, I don't know whether you'll be able to see, but there is a very small seed at the corner. And then if I play, you'll see it growing. Okay. So this is a nice dendrite simulation that we have. Now in this simulation, we would be interested in what is the front velocity. So you can find the average front velocity, that is we have on all of these fronts between the liquid solid interface, it will approximate what is the average front velocity. So here you can see that the velocity as the dendrite is growing, the velocity keeps decreasing. Okay. And then so this was the average velocity, but if you want to find a velocity, say at on this tip, so this is the tip of the dendrite, and if you want to find velocity here, you can click on this velocity over time, and then just enter the start point and the end point. So we will enter the start point as this bottom left corner, and the end point as the right corner.
Endpoint.
So this is a 1000 cross 1000 domain, so that's why I'm entering 1000 comma 0, and then show. And oh yeah, yes.
You can give 900 as well.
Yeah, let's keep 900.
Sure. It's tabulating.
What's going on? Actually, it would come somewhat similar only. But I mean now this velocity is somewhat similar to the plot that we saw earlier. But if I try to take the velocity at the on the diagonal, then you would see that it would be slightly different. So we have the velocity is going to 5e minus 5 here. The 900 cross 900. Okay.
Yeah.
Yeah. So here they are almost very low velocities along the diagonal. So we are pretty well, we are nicely able to capture the velocities in different regions. So you can choose any line that you want, and then you can get the velocity across that line. Next, so in any of the dendrite or the phase field simulation or solidification simulations, we are interested in two most important things. Those are the velocities, front velocities, and then the dendrite tip radius. So next we'll look at the dendrite tip. So we click on this dendrite tip radius, and again we can play this. We can see that the tip radius, you know, it kind of saturates here, slows down, and then again keeps increasing.
Correct.
Right. So that means we start seeing the coarsening happening after this. And so these are the three important things that you could find with the any dendrite simulation. And then that's all for the dendrite simulation. And again, I mean the other things are same. Next we'll look at the front undercooling. file. So here I'll play the simulation, and here you can see that it is kind of oscillating here, that interface between solid and the liquid. So here we are using the shifting of cells. So that means our so we want to observe the interface. So if we are not using the shifting, so in normal conditions, this interface would keep moving in the domain. But if it keeps moving, then the we will have the and if it gets closer to the other end, we would see the effects of the boundary, which we don't want in our simulation. So that's why we keep our frame of reference as the interface, and that's why we will slowly shift the points so that the interface always remains around this point. So that's why you see that kind of vibration here. And now we want to see what is the front undercooling here. So that we can see using this. And again, so we can see that the front temperature, it increases and then again it keeps decreasing. So we'll see continuous cooling that would happen. So because of the latent heat, the temperature would increase and then eventually the temperature would keep decreasing. No? No. Oh, sorry. Latent is not there. Yeah, my mistake. Yeah, it's just the interface motion, and we see the temperature increase and decreasing. So we can have this kind of calculations also. And for this, we needed the temperature. So in the other simulations that we showed, we didn't have this. So the temperature is constant. And then so on. So next thing is, if you have any microstructure, so we'll first close this and then go back. So for the next thing, we need some dummy input file. So this is something that everyone would be interested in, that we have some kind of microstructure, you have some simulation data, and you have microstructure, you have grains, and then you want to see how the coarsening is happening, you want to see where the triple points are, and then how the how many number of grains you would have, and what are the locations of the triple points. Okay. So for that, I'll click on this triple point. And so this part, this triple point calculation and then finding the triple points it has been done by Jitendra Praharaj. And here you can see at the 0 time, we can see a lot of triple points here. Yeah. So at this step, at the first time step, we could see that there are about 27 points. If I go to the next step, you can see they reduce down to 24, 22. And then for each of the triple point that you see, we will have the coordinate or the location of all those triple points. So we can keep a track of where each of those triple points are moving. So I'll play the movie, and you can very nicely see how the triple points are tracked. And then you can see nice coarsening happening. And here you can see you can have the continuous evolution of the triple point locations. And all of this again, you can save as a CSV file, and then you can use it for your further calculations. Let me just check if we have Jitendra online. So he's out of station. So I hope. Okay, Jitendra, are you online? Want to add something? Yeah. Yeah. So I guess he's not there, but I think that's the thing.
If they have any question.
You have anything to add on this?
No, I think that's all.
Yeah. And that's also so we just gave a summary of several tools that we have in the post processing, and then there are some upcoming tools as well which we have planned. That is the interface plotter, shift box integrator, I mean triple point angles, then surface energy calculations, segregation, grain size. So all these are the upcoming features. So right now, just for the representation, we have put it there. You'll see them soon. So any questions on this? Anything else you would like to know? Any questions in the audience? Okay. I guess that's all then. So that's all we have for the post processing tool. And thank you.